The last type of volume we need to talk about computing is one in which you're taking a cross-section of a region or a solid that's been described as sitting in the plane itself. So there's no rotation here, but the method is pretty much exactly the same in terms of how we deal with it. We're going to end up slicing one region or one section of this solid, and then we're going to analyze the volume of that slice, and then we're going to sum up the slices based on the limits of integration. So this, as a mathematician, is a paperweight made so that its base is the shape of the region between the line between the y-axis and the line y equals 4 and the curve y equals x squared, which is shown here on the left. Each cross-section cut perpendicular to the x-axis. That's an important key word. Perpendicular to the x-axis is a square whose base runs from the curve y equals x squared to the line y equals 4. So again, the idea is that this solid, you can't see it. I'll try to put a link in the video or below to give you some sense of what's happening here. But the idea is this: on the left, the solid's coming. It's actually sitting in the plane. It's coming out of the screen right now. And what we're saying is that if you cut it perpendicular to the x-axis like this, you take that slice and then you sort of put your head in the screen and look sideways, you should be seeing a square. So you should be seeing this, right? And so if you imagine slicing it and imagining the slice to have some thickness, you should be looking at something like this. Now the idea is that as you get as x goes from 0 to 2, you can see that each rectangle is smaller, and that means that each square is going to be smaller because the square is determined by the distance between y equals 4 and y equals x squared, and that distance is greater towards x equals 0 and gets smaller towards x equals 2. And so the point is that it's kind of hard to visualize this shape, but if we can just analyze the arbitrary slice, we can compute the volume of the entire solid. So I'm going to call the thickness here dx, because we made a vertical rectangle. Now I have to talk about the sides of this square. Now the sides are determined by, so I'll write the side as s. This side is determined by the height of the rectangle we just drew. So that's going to be 4 minus that y-coordinate of this point, which would be x squared. So the volume of this would be the area of the face, which is 4 minus x squared times dx. And so the total volume would be the integral from 0 to 2 of 4 minus x squared times dx. All right, so same idea. The only difference is we're not rotating, and so we're not imagining a slice that came out of rotating. We're just imagining an object already in the plane, and we're cutting it, and then we're analyzing that slice. Let's do another cross-section problem. Same mathematician, a different paperweight, and it's one in which the base is the same as the one above. So you've got y equals x squared, and you've got y equals 4. And each cross-section cut perpendicular to the y-axis is a semicircle whose diameter runs from the y-axis to the curve y equals x squared. So that means that first of all, we're cutting perpendicular to the y-axis, which means we're making slices like this. Now every time we make a slice and we sort of look sideways into this region, what we see is a semicircle, should have some thickness, and its diameter runs from the y-axis to the curve y equals x squared. So that means that that this distance right here is the same as this distance here. We'll call that d, and that is just that's just this x-coordinate minus this x-coordinate, which is 0. But since I drew a horizontal rectangle, I need to write this point in terms of y. So rather than x squared, I need to write it as square root of y, comma y, which means that the diameter here would be square root of y, which means the radius equals the square root of y over 2, and it means that the volume of this semicircle is pi r squared, which is pi r squared over 2 to get half the half of the circle, times its thickness, which is dy. So this volume here, so the volume is going to be pi r squared divided by 2, so I'm going to put that over with the pi, times the thickness, which is pi y over 4. Over 8 times dy. And so the total volume is going to be pi y over 8. And we're integrating as y goes from 0 to 4.